Hello students, welcome to Vista's Learning. This is Shruti D. Nadiga in Vista's Learning. We provide the quality education for all. We are in 11th standard chemistry. As you know, we are studying about the block elements. I have already started with the 13 group elements and 14 group elements, and we are studying about the last topic, allotropes of carbon. Right? So this is our P block elements with 11th chapter, and it is the lecturing class 5. Here we are studying about the allotropes of carbon. Students, you should know about the isotopes and the allotropes, the difference. Okay, as in the last session I have explained about the difference between allotropes and isotopes. Hope you that. If you have missed any of our videos, you can browse into our web application www.v-learning.in. Got it? Yes. The first point here is that due to the presentation of P pi and P pi bond, we have this allotropes with form, because here the catenation property of carbon. What do you mean by catenation property? Carbon atom can bind with its own carbon atom. How many carbon atoms? 4 carbon atoms. So one carbon atom can bind with 4 different carbon atoms, and that property of binding to its own atom will be called as catenation. It doesn't only form one single bond, it forms a chain or ring-like structure with the carbon atoms, and that property leads to the formation of many compounds of carbon, and that is the position where the structural carbon differs. So we have different structures of carbon bonding to itself, which gives you the allotropes. So here, due to the property of catenation and P pi bonds, see, we have pi bonds of 2 types. So as of now, we have P pi and D pi bonds. Okay, for carbon, we have only P pi bonds. Due to that presence of P pi formation, you will be having the pi orbitals, and they laterally combine and form pi bond, and so we get the pi orbitals. P orbitals combine laterally to form pi bond, whereas they can also combine head-on to form sigma bond, right? So these are the 2 types of bond where this bond is also formed, and that leads to the formation of allotropes. So carbon is able to show allotropic form due to these properties. Carbon exists in many allotropic forms, both in crystalline as well as amorphous. We have 2 types of solids, right? What are they? Crystalline as well as amorphous. Amorphous will be powder, soft powder. It is like talcum powder, whereas crystalline is like sugar or salt. It will be having a exact structure. Diamond and graphite are 2 well-known crystalline forms, whereas you can see the third one is fullerene. It's been discovered by H.W. Krutu, Nally, and Kerr. So diamond, it's a crystalline solid, and it will be having a lattice. Lattice means the arrangement of atoms will be called as a lattice, and here it is having crystalline lattice. In diamond, each carbon undergoes sp3 hybridization. So we know that hybridization of carbon will be having tetrahedral structure, and it will be having sp3 hybridization, where each hybrid orbitals can combine with the adjacent hybrid orbitals of other carbon atoms. Means if I have one more carbon atom here, so these carbon atoms will also have the same hybrid orbitals. So they also form the, for example, this hybrid orbital will combine with this hybrid orbital of other adjacent carbon atoms. So they form sp3 hybridization and link to the 4 other carbons by hybrid orbitals and form tetrahedral fusion. If I have this, and this again links to the other one, this again links to other one, so it will be going on like this, right? So they form the tetrahedral fusion. Carbon-carbon bond length here is 154 picometer, and the structure extends in space and produces the 3D dimensional network of carbon. You can see here the diamond structure is like this, where each carbon atom, if I just take this as a one single carbon and this is attached to 1, 2, 4 carbon atoms. Likewise, if this carbon atom, it is attached to 3, 4 carbon atoms. If I take this, each one will be having same tetrahedral structures and they are interconnected with the other carbon atoms, leading to this rigid body which we call it as diamond. You can see here, these are the 3 allotropes of carbon: graphite, fullerene and diamond. So as we know, these 3 are the isotopes which have differ in physical properties, but they have the same chemical properties. Why does the physical properties differ here, students? Because as you see, the structure varies. Due to that structures, the bonding between each carbon, all are made up of only carbon atoms, but still their structures will be different due to the combination. They are having different structures of bonding. Due to that, they have the different physical properties. So as we say, allotropes of carbon have 2 types, amorphous and crystalline. Here you have in crystalline, graphite, diamond and fullerene, which we consider it as allotropic forms of carbon, which have crystalline form, whereas amorphous form of carbon is carbon black, charcoal and coke. So you should remember this. First we are going with the crystalline and then with the amorphous form. So diamond, graphite and fullerene. These are the 3 things, and let's go with the diamond. Diamond structure, as I said, it will be compact with the tetrahedral structure. This is the tetrahedral structure where each carbon will have sp3 hybrid orbital and they will be linked with the or connected or bonded with the sp3 orbital to form tetrahedral structure with the pico, like 154 picometer as the bond length, and when it is been expanded in the space, we get the 3D structure. So this is the 3D structure which makes the diamond very rigid. Hope you are understanding this, students. Good. And here you can see why diamond will be having high melting point. The diamond has a high melting point due to its electronic configuration in the outermost shell. You see here, we have all the 8 electrons which is around the carbon is bond together, right? Each carbon atom will have 8 electrons in the outermost shell. It is stable. So according to the octet structure, we want 8 electrons in the outermost shell. This carbon is having, each carbon in the diamond or each carbon in the allotropic form will be having satisfying with this octet structure, and they are stable and they don't have any extra electron or less electron to lose or gain, and since they are stable, due to that the melting point of this diamond is high. Got it? Good. So it is very difficult to break extended covalent bonding. You have the covalent bond between diamond carbon atoms, right? So that is not easy to break it down. Diamond has the hardest substance. As we know, on earth the diamond cannot be cut with any other substance. It can cut with only diamond. So such a hard substance is the diamond. It is used as an abrasive for sharpening hard tools. Even for cutting other things also we use this diamond, as it is the hardest substance. It makes it like in making dyes and in manufacturing of tungsten filaments for electric bulbs. You know, right? In the electric bulbs, what do you mean by filament? The bulbs, you will be having this type, right? So this is called as filament. So to produce this or manufacture this filament, the diamond is being. So graphite, next coming with the second allotrope, that is graphite. What is this graphite? This is not like diamond. Diamond is been in the tetrahedral structure with sp3 hybridization. But what about this graphite? It is not the same as diamond. It is very soft compared to that of diamond, right? So its structure is different. Even though it is made up of carbon atoms alone, but still the structure matters. It is having the layered structure. Layers are held by the weak van der Waals force. Van der Waals force are very weaker forces, and that layers, if I have layers, each layer is being held with the van der Waals force, which can be easily removed. To give a very less energy, that force can be overcome. And distance between the two layers is 340 picometer. Each layer is composed of planar hexagonal. Hexagonal means 6 carbon atoms will be combining to give this hexagonal ring of carbon atoms. And the carbon-carbon bond length will be 141.5 picometer. Here, each carbon atom in hexagonal ring will have sp2 hybridization. In diamond, it is sp3, whereas in graphite, it is sp2 and makes 3 sigma bond with 3 neighboring carbon atoms. If you have the hexagonal structure, the one carbon atom will have one, right? And the adjacent one, like if I have one more hexagonal ring, and it will make the bond with 1, 2 and 3. One carbon will have 3 bonds with other adjacent carbon atoms, and so you want 2 plus 1, 3. 3 hybrid orbital, whereas one more pi orbital is present, and that is not or it is not undergoing hybridization, and it will be having a weak van der Waals force with other layer. The fourth electron forms pi bond. So these are the layers where you can see the bond between carbon-carbon atom will be 141.5 picometer, whereas between the layers the distance will be 340 picometer. Now, in these 3 allotropes, we'll study about the graphite. Where do you find this graphite, students? Do you remember the pencil? The pencil tip, we have the pencil lead. That lead is made up of this graphite. Where do you use that pencil? For writing, right? How does the pencil is used for writing? When you apply a very small force, what happens due to friction? The first layer can be easily removed. So the first layer, what you are writing on the white paper, the first layer will be on that. So what happens? The small layer will be on the paper, so you can see what you are writing. Got it? And this layer can be easily removed by the attraction of this other adjacent layer, because it is having a van der Waals force. That van der Waals force is very weaker force, so you can easily read that. So here we'll be having the layers of graphite, where carbon atoms have been hexagonally layered, and they have the 340 picometer, and you can see each layer can be easily. So graphite, electrons are delocalized over the whole sheet. That means, as we say, only 3 hybrid orbitals are there, 1 pi bond is there. That pi bond can be easily moved. The pi electron can be easily localized over the sheet. Electrons are mobile. In graphite, when you have the carbon atom with 1, 2 and this one more, you will be having the adjacent hexagon, right? So this 3. So when you have 1, 2, 3 hybrid orbital and 1 pi bond, here you will be having the electron to move. So they will move from one carbon to another, where we say electrons are mobile. Mobile means move. So graphite conducts electricity along the sheet. Why? Because it can easily jump from one electron to another. What do you mean by electricity? Movement of electrons leads to the electric current, right? So here electrons are present which are free to move. So the electrons are mobile, and hence we can say graphite can easily conduct electricity. Hence it is called as a good conductor of electricity, whereas diamond cannot. Graphite cleaves easily between the layers, that it breaks easily. It is very soft and slippery. It can be used as a lubricant also due to its slippery property. For this reason, graphite is used, that is the same point. It is used as a dry lubricant in machines running at high temperatures where oil cannot be used, because at higher temperatures, if you are using oil as a lubricant, what happens? It can vaporize. So, the structure of graphite, where on the other you will be having this upper layer and lower layer. Upper layer can be easily where it is in the hexagonal structure. Each carbon will be having hybrid orbitals, and the bond between carbon is 145 picometer, 141.5 picometer, and each carbon will have sp2 hybridization, where each carbon will be linked with the 3 adjacent carbon atoms, and one pi bond is free, where that will be formed with the each pairs, and that electrons can be easily moved. Okay, we have pi electron which is not been hybridized, so electrons can easily be delocalized through the structure, and hence it can easily form the or conduct the electricity. Hope you understand this, students. Good. Next we have fullerenes, third crystalline allotrope of carbon. Fullerene are made up of, like it is been synthesized one, you can call it is made by heating. It is made by heating graphite in an electric arc in presence of inert gas such as helium or argon. The sooty material, when you heat something, you'll get the black flame like substance, right? Fume like structure, that will be called as soot. So the sooty material formed by condensation of vaporized CN. CN means carbon with N number of atoms. Small molecules contains, like CN in the sense, in that N, the small molecules or mainly they contain 60 atoms. If you have the sooty material made up of carbon, how many carbon atoms are there? 60 carbon atoms are there. Then we call it as C60 with smaller quantity of C70 and the traces of fullerene consisting of even number of carbon atoms up to 350 or above will be found. So when you take the graphite and use the electric current to that in presence of helium or argon, we get the sooty material which consists of CN, that is C60 or C70 substances. With that we get this fullerene which is consisting of 350 and more even carbon atoms. Right? Fullerenes are only pure form of carbon because they have smooth structure without having dangling bonds. Means without having the dangling bonds, it will be formed with the carbon atoms. So it will be a smooth structure. Fullerenes are cage-like molecules. It will be like football. C60 molecules has a shape like soccer ball, which has been also called as Buckminster fullerene. So this is the fullerene structure. We having the 6 hexagonal shape and pentagonal shape, how we have for the ball. It's a volleyball, right? So box ball, how you have 5 and 6. 5 and 6 likewise we have for fullerene. So you can see 26 membered and 20 membered ring and 5 membered ring will be present there. The 5 membered ring, all carbon atoms will be sp2 hybridized even in fullerene structure, where each carbon will be bonded to the other carbon atoms, like how we have for graphite, and we have the pi electrons in forming the pi bond. So bond length 145.3 picometer, whereas you have bond length for hexagonal and pentagonal. So there it will be having bond length of, so this is for hexagonal one. One 38.0 picometer for pentagon. Right? So it contains 26 membered and 12 5-membered ring. So 26 membered and 12 5-membered ring. As we know, hexagonal will be there and penta structure. So these will be 20 hexagonal structures and 12 pentagonal structures present in the fullerene. So a 6-membered ring is fused with 6 or 5-membered rings, but 5-membered ring can be fused only with 6-membered ring. All the carbon atoms are equal and they all have sp2 hybridization. Each carbon atom forms sigma bond with other 3 carbon atoms, and the remaining 1 electron at each carbon atom is delocalized in molecular orbits, which in turn gives you aromatic character in the molecule. The ball-shaped molecule has 60 vertices and each one is occupied by 1 carbon atom. It also contains both single and double bonds with carbon-carbon with distance 143.5 picometer and 138.5 picometer respectively. Have the spherical fullerenes, which are also called as buckyballs in short. So this is the buckyball structure of fullerene. It is very important to know that graphite thermodynamically more stable allotrope of carbon. That means if you give more heat to graphite, it is more stable. The formation of graphite, delta FH, enthalpy of formation of graphite is 0. It has been as 0, whereas for diamond and fullerene, we have the different values. For fullerene, 360 are 1.90 and 338.1 mole per kilojoules per mole. That means this much energy is been released while formation of diamond and other forms of elemental carbon like carbon black, coke and charcoal are all pure forms of graphite or fullerene. Means they are not purest form. They are impure forms. Carbon black is obtained by burning hydrocarbons. Hydrocarbons means this we will study in the next chapter. Hydrogen and carbon combining together to form a molecule will be called as hydrocarbons. So that will be giving you carbon black when you are supplying the limited supply of oxygen or air. Charcoal and coke is obtained, they are being obtained by by eating wood or coal respectively at a higher temperature in absence of air. So here the graphite formation of graphite is 0, enthalpy of formation of graphite is 0. For diamond and fullerene, we have certain values. Here you can see for diamond it is 1.090 kilojoules per mole. For fullerene it will be how much? 38.1 kilojoule per mole. So when you see these forms of carbon, the carbon, coke and charcoal, these are not pure forms, they are the impure forms. How do you get the carbon black? By hydrocarbons. If you heat them, you undergo incomplete combustion, you will get carbon black, which contains around 98 to 99% of carbon. Whereas the wood, if you heat it in absence of air, then you will get coke. So when that coal is been heated in absence of air, we'll get charcoal. Why, students? Why we are saying that absence of air, absence of air? Because if air is present, it contains oxygen. When we specially say about air, you should understand it is oxygen. If oxygen is there, then carbon, allotropes of carbon reacts with oxygen and produces carbon monoxide or carbon dioxide, the oxides of carbon. So we will not get the other forms what we desire. So we need to take absence of air. So when we take coal and heat it, we'll get the charcoal. What are the uses of carbon? So graphite fibers embedded in the plastic materials form high tensile strength and lightweight composites. So you can form the lightweight composites with this graphite. The composites are also used in production such as tennis, rockets, we have fishing rods, aircrafts and cannons. Being good conductor of electricity, graphite is also used as a electrodes in batteries and industrial electrolysis. Crucibles. These crucibles, I'll show you how it will be. That will be used in the furnace for heating or making ash, preparing ash. For example, I have to find out the minerals present in the certain substance. We weigh the substance and add it in the crucible and keep it in the furnace, so that at a very high temperature, the sample what we have taken turn to ash, and later will check for minerals present in that, which gives you the percentage of minerals present in the given substance or sample. So for that we use crucibles which are at a very high temperature. As we know, graphite can withhold the high temperature. So crucibles made from graphite are inert, dilute acids and alkalis. Being highly porous, activated charcoal is used in absorbing poisonous gases. Yes, obviously porous materials will absorb the gas because they have the space and gas can easily be trapped into. So for poisonous gases to be trapped into, we are using this activated charcoal. It is used in water filters as to filter the water, to remove the organic contaminant. And in air conditioners also, we use this to control the smell. We don't want the bad smell to come out. So what happens? They will absorb the bad smell and can use this charcoals for absorbing the smell. Carbon black is used as a black pigment in black ink also, and as a filler in automobile tires. Coke used as a fuel, largely as a reducing agent in metallurgy. Because coke, when it has been reacted with oxygen, it gives a very high temperature. For that, we are using in metallurgy. Diamond is precious, as we know, that is used in jewelries, and it is measured in carats. 1 carat of diamond will be equal to 200 milligrams. So here we have the visual things, what we just discussed, the points. Same thing, diamond can be used in jewelries, and we can use it as abrasive, sharpening the tools, dyeing and manufacturing the tungsten. Here it can be, graphite can be used as lubricant and in the aircraft, fishing rods, tennis rackets and cannons. So everywhere we are using graphite, and it is also used as a electrodes in the battery. This is the graphite which is used as a electrode in the batteries and industrial electrolysis. These are the crucibles. So in this we'll take the sample and keep it in the furnace. And we have the activated charcoal which is being used for absorbing the gas and removal of organic contaminants from the water. So when the water is being passed through, here we have the activated charcoal which absorbs. Here it is absorbing the smell. It should not get the smelly air outside from the AC. So what happens? It will absorb the bad smell molecules and the charcoal will leave the fresh air. And here we have the ink, black ink pigment which is being produced from this carbon black, and fillers in. To make this black color, we use the automobile tires. And it can be, coke can be also used as a fuel. As I said, in metallurgy, this is the furnace. What happens? The coke will be left and it will react with the oxygen present and it maintains temperature. This is where we use this. So uses of carbon we can see. So it also reduces the metals. If I am adding the coke here and some metals are present which is present in the oxide forms or sulfide forms, what happens? The carbon or the coke, pure form of coke, will react with those oxygen and forms or give out metals. So zinc oxide is reacting with carbon to give you zinc plus carbon dioxide, and lead oxide will react with carbon to give lead and carbon dioxide. So lead and zinc are in oxides forms in the ore, and we can easily remove it by adding this coke. Got it? So coke acts as a reducing agent. Some important compounds of carbon and silicones. Oxides of carbon, we know carbon monoxide and carbon dioxide. So firstly, two important oxides of carbon, that's same thing, carbon monoxide and carbon dioxide. Carbon monoxide, we'll just discuss about it. Direct oxidation of carbon, limited supply of oxygen. Why limited? If you give in excess, what happens? Complete carbon will react with oxygen to form carbon dioxide. So if it is in limited supply, then will form the carbon monoxide. Carbon plus oxygen gives you carbon monoxide. On small scale, pure carbon monoxide is prepared by dehydration of formic acid. What is formic acid? H. Dehydration of formic acid with concentrated sulfuric acid at 373 Kelvin. So what is the formula of formic acid? HCOOH. When that is been heated, so what happens? This carbon monoxide is removed and we have HOH been combining to form H2O. So carbon monoxide is removed from formic acid. Got it? So from formic acid, when it is been treated with the sulfuric acid, we get carbon monoxide removed with the water at 373 Kelvin. So here carbon monoxide, oxygen, carbon and oxygen, where you have triple bond between them. So carbon monoxide, and this is the carbon dioxide, where you can see C present. So carbon can have the disproportionate reaction with oxygen to form carbon monoxide and dioxide. This is the colorless, odorless, and it is nearly insoluble in water. And you can see here one sigma bond and two pi bonds are formed between one carbon and oxygen. So when carbon is reacted with limited supply of oxygen, we get carbon monoxide, which is a gas. So preparation of carbon monoxide, you can see we have a hot coke and steam. When it is been produced, what happens? Steam reacts with coke, and so we get the carbon monoxide because water steam contains what oxygen in that. So carbon reacts with H2O, give out carbon monoxide and hydrogen gas at 273. Hope you can see that blue and black color which is coming out. So that is carbon monoxide, and the orange color one is hydrogen. This can also be done in presence of nitrogen, and we get carbon monoxide with nitrogen gas evolved when carbon coke is reacted with oxygen and get here. The first two things are there, students. First one is that the furnace, what happens? We have coke reacting with water at 273 Kelvin to give carbon monoxide plus hydrogen gas. And the second one is that when carbon is reacted with carbon, oxygen and nitrogen gas, we get carbon monoxide with nitrogen. So here you can get carbon reacting with oxygen with nitrogen at 1273 Kelvin. Then you will get this carbon monoxide with nitrogen. So both side nitrogen is there, but nitrogen acts as a catalyst here. It enhances the reaction, that carbon reacting with oxygen. Should not completely combust, so we are using nitrogen here at 1273 Kelvin. So on commercial scale, it is been prepared by the process of steam over hot coke. As you saw, the steam will be there, coke will be given, and we get hydrogen as a byproduct with carbon monoxide as a main product. The mixture of carbon monoxide and hydrogen gas thus produced is known as the water gas or synthesis gas. You can also call it as syngas. Carbon reacting with water gives the carbon monoxide plus hydrogen gas. When air is used instead of steam, when we are using oxygen instead of steam, the mixture of carbon monoxide and nitrogen is produced, because air contains mainly nitrogen and oxygen. So you can call that as producer gas. What is producer gas? What is syngas? You have to remember. You can be asked for competitive exams also. So syngas is carbon monoxide with hydrogen gas, whereas the producer gas is carbon monoxide with nitrogen gas. Water gas and producer gas are very important industrial fuels. Carbon monoxide in water gas or producer gas can undergo further combustion. They can react further, forming carbon dioxide with the liberation of air or heat energy. Carbon monoxide, its properties, it's colorless, odorless, and almost insoluble in gas. It is a powerful reducing agent and reduces almost all the metal oxides other than those of alkalis and alkaline earth metals, aluminum and few transition metals. This property of carbon monoxide is used in extraction of metals in metallurgy from their ores. So iron oxide, when treated with carbon monoxide, we get iron plus carbon dioxide. Likewise, zinc oxide with carbon monoxide, we get carbon dioxide with zinc. So, the carbon in carbon monoxide has its lone pair, and it can easily give the lone pair to metals. So metals can give the bonds. When it has been reacting with metal is reacting with carbon monoxide, we get the metal oxides. When reacting, get a complex like this, where you can find several metallic carbonyls are being formed. That carbonyl chromium is linked with the other monoxides. Here, this is important, students. We know, is carbon monoxide poisonous or not? We generally say yes, carbon monoxide is poisonous. How do you say it is poisonous? When you see the hemoglobin, generally hemoglobin can absorb the oxygen and give or circulate to all over the body, right? But here what happens, the percentage of oxygen getting absorbed with this hemoglobin and the percentage of carbon monoxide absorbed by the hemoglobin, you compare, the percentage of carbon monoxide which is been absorbed by the hemoglobin is 300 times high. That means easily oxygen can be removed by carbon monoxide and it can occupy that place. So body will not get sufficient oxygen and chances are there for the death. So hemoglobin, if you see here, carbon monoxide plus hemoglobin, it removes the oxygen easily and it occupies the space in the hemoglobin where oxygen is kept. So what happens? We don't get sufficient oxygen. So you can see the heme contains oxygen, and when carbon monoxide is coming, that will be easily removed and they will not be able to have the oxygenated blood throughout the compound we have this. This is also important, students. As we know, in home, if it is producing more of carbon monoxide, it is not good for health, right? So we have the detector also to know the carbon monoxide percentage, how much it is. If it is too much, it will detect and give you the signal. Next we have carbon dioxide. So this is the structure of carbon dioxide, where its physical properties are it is colorless, as we know, odorless, non-poisonous. Carbon monoxide is poisonous, carbon dioxide is non-poisonous. They can easily, like, they have a low solubility in water. 0.03% of the atmosphere have this carbon dioxide by volume. So you can see in the atmosphere we have nitrogen, carbon dioxide and oxygen, where carbon dioxide is having 0.03%. So one carbon will be having the sp hybridization, where each carbon atom will have one carbon atom with each oxygen. It will be having sigma bond, one sigma bond and two pi bond. So one sigma bond each and one pi bond on each. So totally 2 sigma bond, 2 pi bond. So this is the sigma bond which has been formed from one carbon atom and the two oxygen atoms, where they can be easily forming the pi bonds laterally. So you can see this is the sigma bond going ahead with head-on overlapping. So this is the head-on, and we have this formation. Pi bonds are being formed. So two pi, like one pi bond and pi bond. So totally 2 sigma bond, 2 pi bonds are being formed. And here you need to know each pi bond will be having 90-degree difference. So it will be having linear structure from O and the other O having the linear bond. So most important structure is this resonance structure of carbon monoxide, where we know dioxide, where we know each oxygen will be having 2 lone pairs, so they can easily form the resonance structure. So when this is been lone pair is been given on back and vice versa. The lone pair comes on back. So that is the 2 resonance structure have it for carbon dioxide. So you can see here the bond carbon and oxygen bonds are 150, 115 picometer, and they are non-polar molecules. So they will be no having dipole. You can understand doubts? So here these are the resonance which I said. When lone pair of electrons come back, that will give back the electron. Preparation of carbon dioxide, CO2. So here we have CO2 which is being prepared. Carbon directly with the oxygen gives you carbon dioxide, and we have methane. On reacting with oxygen or burning with oxygen, we get carbon dioxide with water molecule. This we call it as combustion of methane gas. So combustion of carbon alone or coke, if you take, both are reacting to give a very high temperatures. So we call it as combustion. Combustion of carbon or carbon containing fuels in air will give you carbon dioxide. So here we can have this one more property, where calcium carbonate, when treated with acid, we get carbon dioxide. Carbon dioxide will be released. So when reaction of calcium carbonate with acid, we get carbon dioxide. Calcium carbonate, when it is been heated also, we get calcium oxide plus carbon dioxide. So when we heat the limestone is nothing but calcium carbonate, we get the evolution of carbon dioxide. How to test the carbon dioxide, students? With lime water test, right? Lime water turns milk when carbon dioxide is added to it. So we have carbon dioxide and water, get carbonic acid. When you add the carbon dioxide to the water, we get carbonic acid, which says that carbon dioxide is acidic in nature because it forms carbonic acid. The property of carbon dioxide. So here carbon dioxide is prepared by complete combustion of carbon and its it containing fuels. So carbon directly oxygen reacting with oxygen to give carbon dioxide, or methane reacting with oxygen to give carbon dioxide and water. In laboratory process, how do? We take the calcium carbonate, add acid to that. So we get calcium carbonate, calcium chloride with carbon dioxide with water. In commercial scale, we heat the limestone where we get the calcium. When we heat the calcium carbonate, we get the calcium oxide with carbon dioxide. So it is a colorless and odorless gas. As we know, carbon dioxide is a colorless and odorless gas and has very low solubility in water and makes immense biochemicals and geochemical potents. Because we have the carbon dioxide, as we know, carbon dioxide is absorbed by the plants to give out the oxygen, and the carbon dioxide which is held or taken in by the plants will be used for production of glucose or carbohydrates, which is very much important for all living organisms. With water, it forms carbonic acid, H2CO3, which is a weak dibasic acid, and it dissociates into two steps. So carbonate, being treated with water, it splits into bicarbonate, and also it can be carbonate. So you have two ions where you can getting this carbonic acid acting with water. So this forms a buffer system which helps in maintaining the pH of blood also, which is having 7.2 to 7.42. If the pH level goes down, then the blood will not easily act. So being acidic in nature, it combines with the alkalis to form the metal carbonate. Carbon dioxide is normally present the extent of 0.03% by volume at the atmosphere, removed from it by the process known as photosynthesis. So if the carbon dioxide is present in the atmosphere, it can be easily removed by the process called photosynthesis. As we all know, photosynthesis, carbon dioxide is absorbed, and in presence of chloroform and sunlight, we get glucose, oxygen with water molecule. So here we have blood, which should contain the pH of 7.26. If it goes lower than that, then the blood will become black, and that will not sufficient. That is not good for health or living organism sustain. So pH level will be maintained by this carbonic acid or carbon dioxide. And photosynthesis, as we know, photosynthesis, the plants contain chlorophyll. They trap the sunlight and they trap the sunlight. So what happens? The leaves contain chlorophyll. They can easily trap the sunlight. In that light or H mu or the photons, what happens? Carbon dioxide and the water which is absorbed by the roots of the plant will prepare the glucose or carbohydrate. So there we are using this carbon dioxide. Carbon dioxide, oxygen to the formation of glucose. Next, what about this carbon dioxide? Here we have the greenhouse effect. When the sunlight is been falling, have the layer of atmosphere which is protecting us. But you can see long wavelengths of the earth radiations can be, but the shorter wavelength can be So for global warming also have this, which increases the global warming. Carbon dioxide increases the warming of the globe and we call it as global warming. We have the dry ice, which the solid form of carbon dioxide, which is for refrigerant in the normal coolings, and even it is been used for the carbonated beverages fire extinguishers because it is heavy than that of oxygen, so it can easily cover on the fuel and it protects the formation of like a combustion by eradicating the supply of oxygen. And even it has been used in the manufacture of urea. Urea is very much important. It is the fertilizer for the substance where we get nitrogen from this urea. Nitrogen is very good because we get nitrogen protein producing plants, or if you take leguminates, they want the nitrogen produce the protein. So how do you get the proteins? Proteins are nothing but the compounds of nitrogen. So if you provide the nitrogen, the urea, then only you can get the protein rich fruit from plants. So we add urea to the plants as a fertilizer which contains nitrogen in that. So the chemical formula, this is the structural formula. Chemical formula is CN2H4O. Yeah. Next we have the friction of this will lead to the electric supply. So we get the electric supply when we are just rubbing it with each other. So we can go ahead with this. By this process, plants, as we say, plants make food or synthesize the food for themselves as well as for the human beings and animals. Unlike carbon monoxide, carbon dioxide is not poisonous, or you can say less poisonous, but the increase in combustion of fuels, fossil fuels, and decomposition of limestone for cement manufacture years together, means for longer years if we are doing production of carbon dioxide, what happens, that increases the greenhouse effect and thus raises the temperature of the atmosphere, which leads to serious consequences. And carbon dioxide can be obtained by solid the form of dry ice by allowing the liquefied carbon dioxide to expand rapidly. So dry ice is used in refrigerant for ice cream and frozen foods. Gaseous carbon dioxide is like extensively used to carbonate soft springs, and we can see that being heavy and non-supporter of combustion, it is used as a fire extinguisher. A substantial amount of carbon dioxide is used in manufacturing of. So in carbon dioxide molecule, carbon atom undergoes sp hybridization, and the resonance is been shown here. Two sp hybridization or hybrid orbitals of carbon atom overlap with two p orbitals of oxygen atom to form two sigma bonds, while the two electrons of the carbon atom are involved in p pi bonding with the oxygen. So the resonance structure will be like this. The electron will be given here, the bond will be shifted. So we'll get, as the loss of electron will get positive here, as the gain of electron will get negative. And that can be again given back, the electron can be come back as a bond, and the bond, triple bond, can be gone back as we get the carbon monoxide. So vice versa, we can do this, the resonance structure of carbon dioxide. This results in the linear shape of the carbon dioxide with the bond length 115 picometer, no dipole moment. Resonance structure. Next we have the silicon oxides. So till now we have studied about the important compounds of carbon. Now we are going ahead with silicon dioxide. So 95% of the earth's crust is made up of silica and silicon. As we know, earth crust, mud if you take, it contains silicon. So we have the silicon dioxide of 95% present in the earth crust. Silicon dioxide, commonly called as silica, occurs in several crystalline forms. So quartz, cristobalite, and we have tridymite are one of the some of the crystalline forms of silicon. There are interconvertible at stable temperature. Silicon dioxide is a covalent and three-dimensional network solid in which each silicon atom is covalently bonded to the tetrahedral manner of 4 oxygen atoms. To have one single silicon, it will be bonded to 4 oxygen atoms. Got it? So with the tetrahedral manner. So each oxygen atom in turn covalently bonded to the other silicon atom as shown in the diagram. Means each silicon, you can see we have one silicon with 4 oxygen atoms here, and this oxygen is linked to this silicon with which is in turn linked with 4 oxygen. So it is linked with the silicon. So it will be a pattern. Okay. If you take this silicon, it will be all will have 4 combiningly, each one will have 1 negative charge, so 4 charge for this structure of silicon dioxide. The entire crystal may be considered as a giant molecule in which 8-membered ring are formed with alternate silicon and oxygen atoms. Silicon in its normal form almost non-reactive because they have high silicon oxygen bond enthalpy, and enthalpy means energy. They have high bond energy. To break that bond we require more energy, so they are normally stable. So it resists the attack of halogen, dihydrogen and almost the acids and metals even at elevated temperature. At different temperature, even though you take the reaction of halogen, hydrogen and metals cannot be easily formed with the silicates. However, it is attacked by hydrofluoride and sodium hydroxide. You can see here when sodium hydroxide is reacted with silica, we get sodium silicate with water, and when sodium silicates are reacted with hydrogen fluoride, we get a tetrafluorosilicon or silicon tetrafluoride with water molecules. Next, one of the important thing with silicon is it forms the quartz. Quartz is extensively used as the electric material. It has made up of it has made possible to develop extremely accurate clocks. Means we'll be having accurate clocks used by the quartz. Modern radio, television, broadcasting and mobile radio communication, all this we are using this quartz. And we have the silica gel which has been used as a drying agent. As it absorbs water molecules easily, it is used as a drying agent and as a supporter for chromatographic material and catalyst. Chromatographic, what happens? We use this silica gel as a plain layer. So on this silica gel will be there. So this acts as a base. So in this, on this base, what happens? It is completely coated with silica gel. Then we have the sample which has been added on that and it starts absorbing. So for base we use this, and Hazelger and allotropic form, amorphous form of silica is used in filtration plants. So this is the way we are seeing from silicates or quartz. Quartz is used for a great accurate clocks, and even in the radio, televisions and all, we are using quartz. For communication purposes, quartz are very. This is the silica gel. You can see this in your packing electricals. Either it might be any of your laptops or mobile phones or any other things will get this gel present, which absorbs the moisture present in the surrounding, and it is also used in industry. So for purification plants also, this, or filtration plants in the sense the place where the purification is taking place. So here are some of the types of silicon. So linear silicon and cross-linked. So what do you mean by silicon? Which is present with the Si with 4 oxygen atoms, right? Instead, if you remove the oxygen and add the substituents there, for example, R are the substituents here. If you are adding that, R2SiO will be considered as the one single molecule, then the replicant of that will form a polymer. So that gives you the linear bonds. If you have this with a linear one, they will get the linear bonds. If it is been branched, one oxygen, again it is been branched with the other. This is the one linear one and this is other linear, and they are again connected. Then that will be called as cross-linked silicons. So silicons, there are a group of organosilicons polymers which are having R2SiO as a repeating unit. The starting material of the manufacturing of these silicons are alkyl or aryl substituents. As I said, R can be alkyl or aryl group. Aryl means aromatic group, alkyl means alkane, alkene, alkynes. So it might be alkyl or aryl substituent which has been present in the silicons. So silicon chlorides can also be used, where R can be alkyl or aryl, where you have RnSiCl as a monomer. When methyl chloride reacts with silicon in presence of copper as a catalyst, if you have the silicon which has been reacting with methyl chloride in presence of copper and at 573 Kelvin, various types of methyl substituted chlorosilicanes of formula monomethyl trichlorosilicon, dimethyl dichlorosilicon, and trimethyl monochlorosilicon with small traces of tetramethyl silicones are being formed. So they are substitutions for when you are reacting the methyl substitutes for the silicones, we get these substances or products. Hydrolysis of dimethyl dichlorosilane followed by the condensation polymerization yields the straight chain of polymers. These are the properties where you can see the properties of silicons. They are waterproofless, means they will not absorb the water. So they can be used as the raincoats. They can withstand the high thermal stability. They have the high thermal stability, high dielectric strength, and they are chemically. So these are used for other purposes. As you see, they are used as sealants. For sealing purposes, this silicones are used. And for greasing, for making as a lubricant also, we use this silicones. And for electrical insulators also, silicon tapes are being used as they are standing the high temperature, and we have waterproof fabrics for raincoats and all, so that they will not absorb the water. And for surgical and cosmetic implants also, we have the silicones. And these are the ores of silicones where we can get feldspar, zeolites, asbestos, and mica. Silicates are found in all these 4 ores. So this is the structure of silicate as we discussed, and it is having the tetrahedral structure and it will be linearly combined. So you can see each silicon will be combined with 4 oxygen atoms, forming the tetrahedral structure. Each will be again linked with the other group of silicates. So they form the continuous chain like structure, which we call it as polymers, and they can form many type structures. So we have the single tetrahedral structures. They can form the ring shape. So here you can see that the silicates can be a linear type. They can form the chain structure or the ring structure by just combining with other silicate molecule. So here we can find this. So it is a tetrahedral chain, whereas this is the tetrahedral ring and above 6-fold, where here we have the linear one. So we can have both. Not only this, we can also have sheet like structure of this silicate. You can see this one sheet, on the other you will be having the layers of sheets which forms this sheet like structure of silicates, where here we have the three-dimensional structure or network for the. So here, as we just discussed about the formation of them, the chain or the polymer, how can you do? Can they take this chain and react, and we get the silicones. Silicones, being surrounded by the non-polar alkyl groups, are water repelling in nature. So that makes them waterproof. So they have in general high thermal stability, high electrical resistance, and they are inert. They generally don't oxidize. They have a wide applications, as we discussed. They can be used in the sealants, greasings, and electrical insulators, and for waterproofing for fabrics. Waterproofing fabrics also be made up of these silicones, as we saw in the video. Being biocompatible, they are also used in surgical and cosmetic. So we have the glass and cement been formed from these silicates, as we asbestos. So this is the structure, one single layer with the hexagon will be having the silicon, and here this can be again replaced with aluminium. So 3 atoms of silicon is replaced by aluminium. Here we generally have 6 silicons, right, where here we replace the silicon with aluminium, where all the silicons will be having +4 charge and aluminium will have +3 charge. So this leads to the variation of electrons, or will be having the holes present, right? So they can conduct electricity. So they were not with the help of metals, sodium, potassium, and calcium, we get this or substance. These are the zeolites. These are porous and they can absorb the substance. So this is the Na2Al2 Si3 O2 is the formation like a molecular formula of zeolite. So where do we use this in cracking units? We use where you can see it can be also used as a ZSM5 for that conversion of alcohols to gasol. So this is the structure where that is the enzyme which is being used in zeolite, which converts alcohols to zeolites, and this is the hard water. Using these zeolites, we can convert hard water to soft water. So you can see here ion exchange reagents will be there, magnesium ions and calcium ions. When hard water is being left, the ions will absorb or attract the magnesium and calcium's. So what happens, as we see aluminium, sodium, like aluminium is being replaced by silicon, what happens, they can easily absorb the potassium, magnesium, and calcium. So what happens here, they can easily attract the ion exchange resins can easily attract these ions, and so soft water can be thrown out. So for conversion of hard water to soft water, lights. So by this we finishes this chapter, students, P block elements. Hope you understand all things. you have any doubts, you can get back to us. As we always say, Fast Learning provides you the quality education. We also have provided with other languages also. If you are having any of your siblings who are interested in watching the videos in their own language, you can browse into our web application and get it. So you know our web application, I guess, that is www.learning.in. Thanks for watching Vistas Learning.